Hello everyone, I'm Juho from Yonsei University, and it is a great honor to present my study here at EC3 conference. Today I'm going to present symbol recognition in piping and instrumentation diagram via mask-aware template matching with spatial similarity. Some of you guys are familiar about P&ID. Let me start with the background. P&IDs are core engineering drawing in plant industry. They represent equipment, piping, and control system through symbols. P&IDs are created with CAD tools where each symbol is managed as a block. However, as you can see here, they are often shared as rastered images. So the symbol semantics are lost. As a result, P&ID review still relying on engineers, making it time-consuming, labor-intensive, and prone to human error. And there is a second problem. Symbol geometries and labeling conventions vary across projects. Due to this variability, fixed rule or model fine-tuned on specific dataset fail to add to new project. So we need to recognize symbol in rastered P&ID images with lost semantics while adapting to symbol system that vary by project. To handle this challenge, object detection model have been actively studied. This model can predict both location and the class of the symbol. However, as this diagram shows, they require retraining whenever new symbol appear. So every new project means building a new data set and retraining, which is significant burden. More recently, visual language model have been explored. VLM requires no additional training and are easy to use. They do understand symbol, but when we ask for the coordinate of symbol, it fails due to limited spatial reasoning. As you can see in this picture, some symbol location is not fit well. It's not fit. So we have two limitations. Object detection model localize well, but need retraining. VLMs need no training, but cannot localize. To overcome this limitation, we propose a symbol legend-based template matching using region of interest mask and intersection over union similarity. It has two key ideas. First, no additional training is required. When new symbol appear, we just need to follow the legend. Second, accurate symbol coordinate are derived by evaluating pixel level spatial similarity. And this flowchart shows the overall pipeline, and I will explain more on the next slide. The first step is pre-processing. Target symbol are selected from the symbol legend to construct templates. Since symbols appear in various orientation and size, so we applied rotation and deduplication, then flipping and deduplication, and scaling step by step. Next, we extract ROI masks. The Convex Hull algorithm finds the smallest polygon, including each symbol. This gives us the actual region of each symbol occupies. And ROI masks are used in the next step to mitigate the impact of irrelevant line and text around the symbol. Here is how the refinement works. The reason overlapping the symbol template on the P&ID is defined as a P&ID patch. The symbol templates ROI mask and the P&ID patch are convoluted to keep only the actual shape of the symbol. Next, let me explain the template matching process. Each template slides over the entire P&IDs pixel by pixel, and we compute IOU between template and refined patch. If the IOU exceeds the threshold, the patch is stored as a symbol candidate. The final step is post-processing. We introduce intersection over minimum based non-maximum suppression. NMS is a technique that keeps only the best among duplicate instance, typically using intersection over union. NMS However, inclusion relationship are common in P&IDs, and IOU-based NMS cannot deduplicate the candidate. For example, when candidate A contains candidate B like this, then IOU-based NMS computes a score of only 0.35. So the duplicate survives. But with IOM-based NMS, the score is 1, and the duplicate can be successfully removed. Now let me show how we set up experiments. A total of 16 templates were selected from the symbol legend as targets. Then all symbols were pre-processed, resulting in 198 symbol templates in total, shown on the right side. All experiments ran on desktop PC with a core CPU worker. And we used 4 real-world plant P&ID for actual chemical plant projects. And these high-resolution images, about 20,000 by 15,000 pixels, containing 353 target symbols in total. And we compare our method against conventional template matching, which is cross-correlation, correlation coefficient, and skew difference, which evaluate similarity as a pixel intensity. The first experiment is efficiency, and our method was the slowest. This is due to the additional ROI convolution operation. But in the second experiment, our method achieved the best F1 score at the 0.85 threshold, outperforming all baselines. And there are 2 reasons. The ROI mask removed the influence of line and text included in template margins, and evaluating spatial similarity than pixel intensity is more accurate for P&IDs. And our method successfully recognized most of the symbols. However, we observed some failure cases in 3 types. Missed detection occurred when similarity fluctuated around the threshold, or when symbol deformation exceeds our pre-processing range. And false detection occurred in inclusion when a smaller symbol with a high IOU, it is recognized instead of the larger one. I say the conclusion. In this study, we addressed the challenge of recognizing symbol in restored P&IDs and handling symbols variation. We propose a non-learning based template matching pipeline combining with ROI mask and IOU matching and IOM based NMS. And it achieved an F1 score of 0.992 on 4 real-world P&IDs. And these results support design checking, datasheet linkage, and revision management, contributing to the P&ID digitization. Of course, this study has some limitations. First, template must be constructed manually, so we plan to automate template construction from the legend. Second, detection is sensitive to the threshold, so we will consider integrating geometric similarity metrics. Third, the pre-processing time is so long, so we are explore algorithm optimization and use GPU-based parallel pre-processing. And finally, large symbols are sometimes misdetected as smaller ones. So we will prioritize larger symbols during pre-processing. Despite this limitation, our method offers a practical training-free solution for the plant industry. Okay, I will end off my presentation. Thank you for listening.